And here's a sort of table of some VLSM data that I made up. This is not real data, of course. But you can imagine a table like this, a much bigger table that describes your VLSM study. So in each row is a voxel, and in each column is a subject. And on the bottom there, I just put in the scores just for the fun of it. And what you can see in this table is that voxels 4 and 5 are actually identical. There's no way to distinguish these voxels. They're lesioned in exactly the same subjects 2, 5, and 6. Voxels 1 and 2, in fact, differ only in one subject. Actually, that's a big difference because there are only 6 subjects. But if there were 150 subjects and they only differed in one subject, those voxels would be very similar. And the t-values you observe in those 2 voxels would be very similar. And most likely those voxels would be neighboring voxels. It would just be next to a boundary of where one of your subject's lesions lies. And the color of that voxel on your SPM map or your SPM would be very similar. If one was bright yellow, the other one would be probably roughly the same shade of bright yellow. The other thing to notice that I'm not going to talk about much is that voxel 2 is actually redundant with a combination of 3 and 6. If you observe a relationship between voxel 2 and behavior, it's entirely possible that that pattern of behavior could easily as well be explained by the combination of voxels 5 and 6. So here's that new figure that I was really excited about. Here's what happens. What happens is you end up with lots of voxels in tightly packed clusters, like these. I tried to color code it so that voxels that with the same pattern have the same color. So the idea is that all these bluish voxels right here, with this shade of blue, are lesioned in exactly the same set of subjects. If you want to tell the difference between, if you're really interested for some theoretical reason or some anatomical reason between this little chunk of cortex and this little chunk of cortex, well, you've got to find a lot more subjects that have a lesion that, ends right here, because right now you have none, and those voxels are all exactly the same. What you really have there is one large irregularly shaped voxel, or I guess you can call it a region. What? Did I get this backwards? Yes. This should say 86 and that should say 20. Fortunately, I didn't talk about that yet. What happens is this introduces a kind of smoothness to your data. What happens is the fewer subjects you have, the smoother it is. So if you only, this is actually really the same set of subjects. In that case, I just looked at the first 20. It's the same data set. If you only have 20 subjects, then the area over which you can't make any sort of discriminating inferences, the areas have gotten larger. And the area is probably even larger than what you see there because it's a three-dimensional volume. We're only looking at one slice here. So this kind of coherence is a sort of it's a fundamental limiting factor with VLSM. But what's as important to understand is that the difference between neighboring regions here, and the differences between neighboring regions are very, very slight. And what you can do, and what I've done here, is plant a flag in one voxel somewhere there in the posterior temporal lobe, and looked at the correlation, so Pearson's correlation between that voxel, the pattern of lesions in that voxel, and the patterns of lesions everywhere else. So a high correlation means if a subject's lesioned here, it's lesioned there. So as you can see in this neighborhood, I think this is from about 55 subjects. As you can see in this neighborhood around my little crosshairs, there's a really high correlation. It's not quite 1 actually, except right around here, but there's a really high correlation. And in fact, there's no way you're ever going to tell anything different about these two voxels. And obviously, if you're carrying out a statistical thresholding procedure, the line has to get drawn somewhere. But for the most part, you have a sort of very large area that has, for all practical purposes, the same information. And if you really want to be able to identify differences between this area and this area because it's of great theoretical interest, then you're going to need vast amounts of data. What's also striking here is that the voxel where the crosshairs are has lesions from 3 out of 43 patients in this case. It happens to correlate really well, an R of 0.56, with a group of middle frontal gyrus voxels damaged in only 1 patient. That's I guess most of this orange area up here, I think. So because that correlation is very high, there's the possibility that if that one patient happens to perform really poorly on some test, for unrelated reasons, for whatever reason, you're not only going to associate that pattern of performance with this area up here, which is where that patient is damaged, and that may be what's actually driving the effect. You're also going to associate it with what's back here because they're very highly correlated. What's worse, you may be thresholding your lesion analysis in a way that you don't include voxels that are only lesioned in one subject. So you may actually see a map that only includes this area that shows no relationship up here because you've eliminated voxels with only one patient, but where the effect is completely driven by what's up there in the middle frontal gyrus. So this spatial coherence issue can really challenge how we interpret the data. And in fact, this is a problem that does not come up as much in fMRI. fMRI data can be smooth, but it tends to be locally smooth. You rarely have distant correlations that aren't meaningful at some level. So, and the sort of level of smoothness of this map is affected by all sorts of things, not just the number of subjects, but also particular qualities of the patient population, inclusion-exclusion criteria, things like that. So, I guess what I would say in summary about this is that spatial coherence really affects everything having to do with lesion analysis. It affects your power calculations. It affects how you carry out the analysis, how you correct for multiple comparisons. It affects which questions are answerable in your data set, and exactly what kinds of interpretations you can make of the results. So it's something to really try to understand. Not that I feel that I understand it yet, but something to try to. We're at 5 o'clock. What are our time?
Yeah, we're at 5 o'clock. That's a shame. Okay, so all those plans for what was going to happen at the end of the session, they're gone now.
Well, imagine you walk into a room and you see some computers. That's what it'd be like. Oh.
So, well, we need to. Okay, so we can hold off on the discussion of what other things we want to do until we have some more experience with VLSM. That I think is fine. You can always send me emails if you want to communicate that, and I'll tabulate your suggestions. What I am more concerned about is getting people up on the cluster who want to be. So let me ask you this: the next session is next week. Is that right?
I think it's 2 weeks.
Oh, it's in 2 weeks. Okay. So and we don't have any homework this week.
Well, there was one homework item for this week that I wanted to give people, which is to somehow, some way, become familiar with Linux. Because the analysis cluster runs Linux. Read a web page, do something. But those of you who are here, try to get an account on the cluster. Those of you who are at Penn, try to get an account on the CFN cluster if you don't already have it. Obviously, there are many people in this room who are already perfectly comfortable with Linux and you don't have any homework.
Okay, so the third session where we talk about registration, I'll go into a little bit more about
using Linux.
Using Unix.
Unix. Yeah.
That
that's
is going to be heavily important.
Okay, so that's great. Let me ask this: you know how to get people signed up onto the cluster?
Making an account.
Yeah.
That requires super user privilege, and I don't have it. Steve can do it.
Is that what's required?
Yeah.
So what's required to get people accounts on?
They should email Steve
Steve Day.
And I actually let me. What I was going to do. Let me see if I put the address up here somewhere. Oops. So ignore this about the virtual machine. But I am going to put stuff related to this workshop series at this web page. Actually, that just redirects you to another web page. But if you go to this address, voxpo.org/VLSM, I'm going to put information there that has to do with getting accounts. And for those of you who don't want to get an account here or at Penn, or who would like to just try stuff at home, I'm going to make available a virtual machine that you can basically install and run on your own computer. It's fairly easy, but it does take a long time to download because it's like 2.5 gigabytes.
But other people can use it. I mean, for people who are going to be using the machines here or the cluster here or the cluster at Penn won't need the virtual.
Right, unless they want to try stuff at home.
Unless they want to try stuff at home. Okay. So we can get you up and get people accounts here by just going through Steve, and then we can go further and see what questions arise. Okay. Good.
Let's see. So this page has what looks like the beginnings of information about some stuff, and I'm going to try to update it again tomorrow to actually put the virtual machine there in case anybody does anybody actually think they might be interested in the virtual machine, because it takes a while to upload. Anybody?
I may at some point.
You already have, so you need like VMware, like
Yeah, well, VirtualBox, but it's the same. Yeah, it's all free software. But
certainly
okay.
be useful for homework, and there are going to be homework assignments as
Yeah.
we go along.
And we talked about possibly people coming in to follow along on their laptops. It's on for some of these later sessions, so it would be helpful for that if you wanted to install a virtual machine on a laptop. But it won't be required. We're not going to make everybody bring in a laptop and
No, there's no room. Okay. Good. Any other questions or suggestions or anything like that? Do we expect most of you back next for the next session? Yeah. So we need to figure out. So the room is going to essentially be filled in the way it is here. So that means we're not going to have tables. Okay. As long as we know. Good.
Thank you for coming.
Okay. Thank you.